Hi everyone, my name is Ayushi and I'm a third year PhD student in Abbott Research Group. Today I'm going to give a poster presentation on my work titled Using Liquid Crystals to Study Nitrogen Dioxide Adsorption on Anatase Surfaces. One of the major scientific challenges is elucidation of processes which amplify specific atomic scale events into macroscopic scale. In this context, liquid crystals are an important materials because the orientation of molecules can be changed by subtle interactions between mesogens and chemically functional surfaces. Specifically, this study aims to explore the anchoring behavior of liquid crystals on metal oxide surfaces and study the catalytic adsorption of NO2 on titania using techniques such as polarized optical microscopy and X-ray photoelectron spectroscopy. As suggested by past catalytic studies and our XPS characterization, we found that there are two reactive binding sites for liquid crystal anchoring on titania surfaces, namely the undercoordinated 5-fold titanium sites and the surface hydroxyl sites. We first hypothesized that hydrogen bonding interactions between surface hydroxyls and liquid crystals occur and control the anchoring behavior of liquid crystals. And to test this hypothesis, we used liquid crystal mixtures with hydrogen bonding strength dependent on their terminal functional groups. We used nitrile functional group, pyridine, pyrimidine, ethoxy, and fluorine terminated functional groups liquid crystals. And we found that strong interactions between surface hydroxyls and nitrogen containing functional group liquid crystals lead to homeotropic anchoring, which is characterized by dark appearance of liquid crystals under optical microscopy, whereas for ethoxy terminated liquid crystals, strong hydrogen bonding interactions lead to tilted anchoring characterized by bright appearance of liquid crystals. Moreover, adding a competing dopant molecule such as dimethyl sulfoxide, which binds much more strongly than the nitrogen containing liquid crystals, this molecule disrupts the homeotropic anchoring of nitrogen containing liquid crystal molecules on titania and leads to an anchoring transition, which is characterized by dark to bright optical change. We also found that in mixtures of liquid crystals, anchoring is governed by the anchoring behavior of stronger hydrogen bonding molecule, such as in a mixture of 5Cb and the ethoxy mix. We knew that the ethoxy mix binds strongly than 5Cb, and therefore in a mixture of ethoxy series and 5Cb, the anchoring behavior of this mixture is determined by the anchoring behavior of the stronger binding ethoxy mix, which is tilted in this case, and therefore for the mixture also we observe a tilted anchoring. Our LC system using 5Cb as the liquid crystal mesogen also reports the catalytic reaction of adsorption of nitrogen dioxide on titania and formation of nitrate species on the surface. We found that the optical response of the liquid crystal is dependent on the surface concentration of nitrate formed on the surface. For higher concentration of nitrate formed on the surface, we observe planar anchoring for the liquid crystal. However, for lower concentrations, we observe homeotropic anchoring of the liquid crystal. So, in summary, we concluded that hydrogen bonding interactions between functional groups of LCs and titania surface hydroxyls underlies the observed anchoring behavior of the liquid crystals on these metal oxide surfaces. Further, the response of 5Cb liquid crystal to 10 ppm NO2 gas is dependent on the surface coverage of the nitrate species formed. Further, our future efforts will focus on leveraging opportunities in the field of titania as a photocatalyst and developing photoresponsive liquid crystal systems. With this, I would like to thank our funding source, National Science Foundation's DMREF program, and thank you everyone for listening to my talk.